Welcome. The topic of this session is how to tailor the Google Dataproc configuration to reduce the Spark execution time and cut the Dataproc service cost. We will start by first introducing the problem of tuning the Dataproc configuration. We will then discuss the approach we implemented at Akamas to solve this problem by providing a real-world example. Finally, we will conclude by sharing some takeaways. Before proceeding, please allow me to introduce myself. My name is Luca Chiabrera, and my role at Akamas is Head of Sales Engineering. I spent my whole professional career working on performance engineering topics. Let's start by discussing the problem, and actually by first providing a short and oversimplified introduction of Spark. Spark is an open source framework used mostly to process big data workloads. One of the benefits of Spark is that it simplifies managing the complexity of parallel computing, such as data partitioning, job scaling, and fault tolerance. From an infrastructure perspective, Spark is deployed as a cluster with one master server and multiple workers. In our session today, we are going to focus on the challenges of managing a Spark cluster and optimizing the executing of Spark. Indeed, one of the biggest challenges in working with Spark is managing the cluster itself. Setting up a cluster from scratch and configuring the various components are labor-intensive and time-consuming tasks. Similarly, modifying an existing cluster, for instance, by scaling it or by shredding the data or reconfiguring the components, also require significant time. The complexity in creating and modifying the cluster typically leads to having one or few costly clusters that remain idle most of the time, just waiting for the next job execution. Last but not least, right-sizing a cluster by identifying the best hardware configuration for the master and workers, and the best Spark execution parameters need to be done for each Spark job. This means that the best configuration for all these parameters strongly depends on the workload that you need to process, while most of the time, a single cluster and a Spark configuration is used for many different jobs. Now, it is true that Google provides Dataproc, a fully managed service that addresses most of these challenges. For example, Dataproc solves most of the complexity related to Spark cluster management, and due to the short time needed to spawn a fully operational cluster, enable an on-demand approach to the cluster execution. However, the four major challenges remain. That is, even with Dataproc, you are still have the responsibility of right-sizing the cluster, identify the best hardware for running each node, and the best job execution parameters. And all these configurations have a direct impact on both execution time and cost of the Dataproc service. Now, the problem is that tuning this configuration is really complex. We can quote here the famous High Performance Spark book, where they state that this is more an art than a science. Tuning Spark execution parameters is really tough due to the many factors that need to be considered and the fact that the configuration itself is strongly dependent not only on the specific job, but also on the cluster characteristics. Similarly, finding the best configuration of a cluster in terms of number of nodes and hardware configuration is strongly dependent not only on the job, but also on the Spark execution parameter. Working on both these dimensions at the same time make the complexity of the problem grow exponentially. So each time you execute a job, most likely you are wasting time and or money due to a non-optimal configuration. This complex problem requires a new approach. At Akamas, we have identified 4 key requirements that we believe are required to effectively solve this class of problem. First, the new approach should allow a full stack optimization, meaning that it has to be able to optimize several different technologies at the same time. The optimization cannot focus only on Spark parameter or on a cluster definition, but has to identify the best parameter for both layers at the same time. Second, the new approach should allow a smart exploration of the space of potential configuration. If we consider all the possible value for all the possible parameters, we have billions of possible configurations. So a brute force approach is simply not feasible and would not work for this kind of problem. To be effective, a solution needs to be identified in a reasonable time frame and in a acceptable cost. Third, the new approach should allow us to align to each specific need, priority and use case of interest by defining custom optimization goal. For example, in some cases, the user may want to reduce the Spark execution time to deliver business-critical data as soon as possible. For other users, the cost could be the key driver for the optimization. And last but not least, the new approach should be fully automated to ensure a reliable process and the fastest convergence to the optimal solution. At Akamas, we adopted a fully automated machine learning-based optimization that satisfy all these requirements. In particular, we leverage specific machine learning technique known as reinforcement learning, which are suited for smartly exploring huge combinatorial spaces of possible configuration in a short time. These figures show the 5 phases of the automated process. The first step is to apply a configuration to the target of the optimization. The second step is to apply a workload to the target so as to assess the impact of the applied configuration. The third step is to collect KPI related to the target system. That is information, data, and metrics about the behavior of the system under the workload. The fourth step is to score the configuration against the specific goal by leveraging the collected KPIs. The last step is where the machine learning kicks in, by taking the score and the tested configuration as input, and by producing as output the most promising configuration to be tested in the next iteration of the same process. In a relatively short amount of time, the machine learning algorithm learns the dependencies between the configuration and the system behavior, thus identify better and better configuration. This fully automated process enables a new performance tuning process, where the user defines the optimization goals and constraints, and then lets the machine learning-based optimization to automatically identify the optimal configuration. Let's see how this new approach applies to our real-world example. For our real case optimization, we leverage TPCDS, an industry standard benchmark that is used to evaluate and compare the performances of different processing engines. We executed several optimization studies based on different goals, and we then compare different configuration of Dataproc cluster and Spark execution parameters. As I said before, Dataproc allowed to easily create a Spark cluster and execute Spark job. Moreover, thanks to the Google Cloud CLI, it is possible to define a fully automated and repeatable process to execute the benchmark by first creating the cluster, then loading the data from an external data store into Hive, executing the benchmark, launching the Spark job, and finally deleting the cluster. Once that the benchmark execution process is automated, the implementation of our machine learning-based optimization is pretty straightforward. In the apply configuration step, the configuration files corresponding to the cluster and the Spark job parameters are generated. The cluster is deployed using this configuration file, and the data are loaded into Hive. In the apply workload step, the benchmark is executed using the Spark execution parameters provided in the configuration file, and then the cluster is deleted. In the collect KPI steps, metrics related to the duration of the job and the cost of the cluster are collected. And in the score versus goal step, the score is computed based on the collected data and compared against the defined goal. In the machine learning-based optimization step, the next configuration is automatically identified by the machine learning algorithm based on the score of the previous iteration. Let's now move on to the actual optimization and result that we have been able to achieve. The first optimization study had the goal of identifying a configuration that reduces as much as possible the duration of the benchmark. As you can see, the results are quite interesting. Our machine learning-based optimization identifies a configuration that reduces by 55% the duration of the benchmark. However, this configuration has a downside, as the actual cost of running the cluster would be increased by 52%. Let's have a look at the configuration identified by the machine learning-based optimization to better understand what happened. On the left, we have the baseline configuration. That is the default configuration used by Dataproc for running a Spark job, representing the minimal and cost-effective cluster configuration suggested as default in the Dataproc documentation. On the right, we see the optimized configuration, where we can notice two main changes. The suggested instance for the worker nodes is way bigger. That is 8 CPU, 32 gigabytes of RAM versus 2 CPU, 8 gigabytes of RAM. The suggested configuration for the Spark executor in terms of number, cores, and memory is completely different. We went from a fat executor setup, where there is one executor per node, to a thin executor setup, where there is one executor per core. Since the new worker instance was way more powerful, but also more expensive, the final cost increased as well. As said, the results are interesting, but not impressive, as the machine learning-based optimization suggested increasing the hardware and thus the cost to get the job done faster. But what if we now add cost constraints to our optimization? So we defined a second optimization study with the same goal of the first study, but with the constraints that the optimal solution should not exceed the baseline cost by more than 10%. As you can see, the results are now very impressive. The machine learning-based optimization identifies a configuration that reduces the duration of the benchmark by 47%, while increasing the Dataproc cost by only 3%. This is a way more interesting result than the previous one. Let's now have a look at this new configuration. Again, on the left, we see the same baseline as before, and on the right, the newly recommended configuration. This time, the recommended node is smaller, that is just 4 cores and 16 gigabytes, with respect to the 8 core and 32 gigabytes of the previous configuration. But the CPUs are now based on a more recent technology. Each CPU is more powerful and slightly more costly. At the same time, also the executor configuration has been changed. Now we have an executor per virtual CPU, the hyper-threading is enabled on those nodes, and each executor uses less memory than in the previous configuration. We then decide to move to a different goal by focusing on optimizing the cost. As you can see, also in this case, the results are quite significant, as the machine learning-based optimization identified a configuration that reduces both cost and job duration. Before analyzing the result, let's clarify that the cost of the Dataproc service are mainly driven by two factors. The cost of the node using the cluster and the cost of the service itself, that is computed by taking into account both the total number of cores in the cluster and the cluster running time. Both these costs are billed per minute. So shorter is the job execution, less time the cluster run, and lower is the cost. So there is a clear relationship between job duration and cost. Yet, identifying a configuration that reduces both cost and job duration is not exactly trivial. Let's look at the configuration detail. Again, on the left, we see the same baseline as before, and on the right, the newly recommended configuration. This time, the worker node is pretty small and cheap, but likely this hardware configuration is only valid for the benchmark that we executed. At the same time, the Spark execution parameters were tailored by considering both cluster and job workload at the same time. This is what really makes it possible to achieve such an impressive saving in terms of both time and cost. All right, time to conclude with our takeaways. Our first takeaway is that tailoring Spark and Dataproc configuration is a complex problem that cannot be solved with a traditional tuning approach. A second takeaway is that we need a new approach to be able to efficiently solve this class of problems. We have described the key requirements for this machine learning-based optimization that we refer to as autonomous performance optimization. Finally, We have demonstrated that this approach works. We were able to automatically tailor Spark and Dataproc configuration to reduce Spark execution time while cutting Dataproc service cost. Many thanks for your time, and please send us any comment and question by leveraging this contact.
Thank you so much, Luca. It's fascinating how much I think it's a sign of how complex the software industry has become, that now we have to start doing ML and AI to help us basically optimize the work we do. All right, let's see what questions we've got. Let's start with the first one. So I like to point out the configuration challenges, and I was wondering, have you guys encountered also the fact that there is a seasonality, right? So usually the volume of data might change. Maybe your 8 o'clock in the morning run will be half the size of the run at 12 o'clock or something like that.
Yeah,
How do you deal with seasonality?
For my experience, this is particularly relevant for online services where you have within the same day completely different load level workload on the application, different kind of user and different kind of behavior also from user perspective that could require a specific optimization for the workload, because at the end the optimization, the configuration is tailor-made on a specific workload. So a way to manage this could be, okay, let's focus on the worst case, which will be the worst from a workload perspective, from a load perspective, which is the worst case that we have to manage. So we can prepare for the worst, and it's something that it's common to, I would say, the performance testing approach, where you have to run a performance test to validate your application, and usually you try to test the Black Friday, I would say, workload condition. And the benefit with machine learning is that you are really fast in exploring the optimization space. So you can adapt, maybe not yet in a single day time span, but if you are talking about weekly seasonality, you can run your optimization really fast and find the best optimization for the new workload. So the machine learning allow to have result in a super fast way with respect to the traditional approach, where you can spend weeks, months in a single optimization. So also allow you to keep the pace of the evolving workload over time. And with Spark, it's not mostly the workload. The main challenges on the data set that can change, and also in this case, the worst case approach is the first, I would say, solution that would apply to deal with the workload evolution over time.
Okay, so basically by preparing for the highest workload, then afterwards you think it's just linear scalability that will kick in, and that's kind of by design what Spark brings you to the table. So
yes, exactly.
Yeah, the parameters should kind of stay the same. All right, that makes sense. Moving on, our second question. All right, I like the collect KPI part, and I was wondering, to what extent, when you run this on top of Google, but I guess all the other cloud platforms, to what extent you actually get to the metrics you really need to be successful? Are they giving you all the data you need, or do you think they should give you more?
Okay, so I would comment in two points. The first one, no, they don't give you all the information that you would need for a traditional and human optimization, because you need to understand the data, you need to go through the different metrics, KPI, have a clear understanding of the different pieces and layer of your architecture or of your stack are working. With the machine learning, the good point, especially with the reinforcement learning approach, it's a kind of magic. So in inputs, the information that the machine learning requires are really few. I just say a single one, so the score. And based on the score, it's able to understand how the parameters that are managed by the machine learning are affecting the score itself. So at the end, you need just one single KPI, one single metric to drive the whole process. For sure, as I said during the presentation, you can add also constraints to be sure that the optimization is meaningful. It's, I would say, in a safe space from a functional perspective, from any of the requirements that you can have in your optimization. But the machine learning per se just requires a single score, the single score that can be a matrix. Maybe you can combine multiple metrics, but to be able to have an optimization based on this approach, you just require very few metrics Even if it's, I mean, with my background, I guess with most of the attendees, it's not so easy to accept that with few data you can get this kind of result. We like to go through the data, the metrics, see how they behave. But machine learning, it's something new, something different. So few metrics.
Exactly.
Yeah.
It's counterintuitive, but I guess you're doing it, so it must be working. But yeah, it's true. It's counterintuitive because in a way you're using the machine learning to basically fight any opacity that the big platform, cloud platforms will stand in front of. Impressive. Third question: you've seen that we are a bit skeptical of benchmarks. Not skeptical, but we tend to recognize their limits. So
Yep.
I couldn't skip the opportunity to ask you about how representative is this TPC-DS benchmark for the real workloads you see.
Let's see. That is the best that you can find.
Okay,
and again, as we said before, after the first question, each optimization is workload specific. So the optimization that I presented is specific for TPCDS, and so let me say that it proved that this approach works for this specific workload. If you apply a different workload, you will have a completely different optimization, but the approaches will be exactly the same. So the idea of picking a benchmark was to use something that is known, that is reliable, that is meaningful somehow, without having the complexity, because building a Spark cluster, create a data set, create all the Spark job is not easy. The benchmark simplify a lot all these kind of tasks that need to be performed to be able to implement such optimization, and it's used as industry standard for this kind of analysis. So it's reliable, but at the end the optimization was specific for this specific kind of benchmark and workload. But it's the best that you can do, I would say.
Yeah, and okay, I think that's definitely fair, and this ties in nicely with the last question we had, which was really the model. If you train a model on a benchmark, can you just take the model and apply it to any other workload? And I think the answer from what you said is no. You have to train the model to the workload.
Yeah, let's say that with the reinforcement learning, each optimization you start from scratch. So you're not building a model that you're going to reuse on different workloads, on different optimization. And the point is that with specific algorithm, you can solve the problem really fast. So for instance, I didn't mention it in the speech, but the optimization that the tree optimization that I implemented required just 30 experiments, so 30 iteration of the benchmark to find the optimization. So it's not that much time, and you can execute the same kind of approach on different workloads. So not having a model that you reuse, you start from scratch each and every time, but you are fast. So the machine learning with this approach, it's really fast to find the best configuration.
And just out of curiosity, I'm curious about the cost reward. So how many ML training runs you need on a specific workload to get a model that is efficient? And do you see the ROI coming fast?
Let's say that the number of iteration depends on the complexity of the problem. And the complexity of the problem, it's the problem itself. So if you are trying to optimize in something that is well optimized, it's a complex problem. If you start usually from default, so you start from scratch, no one has optimized the configuration before applying this approach. You have an higher optimization space, so it's easier to explore this space. And the other aspect that affect the complexity and time is the number of iteration, is the number of parameters. So if you add more parameters, more parameters you have in the optimization, more complex is the space that the algorithm have to explore. So just to give you a rough number, if you are talking about 10 to 20 parameters, usually 50 iteration are enough. If you go over 20, you go around hundreds of iteration. But it really depends also on the workload and the complexity of the problem. And so that's another relevant topic with respect to the parameters is that they can belong to different layers. So as I show you, optimize it concurrently, the Dataproc layer and the Spark layer. So usually you have to do a layer-specific optimization because you have the Spark expert and maybe the Dataproc expert. While with machine learning, those are just parameters. the machine learning is not even aware that are coming from different technology, and they are just knobs that you can tune. So adding layers is not necessarily increase the complexity, but adding parameters increase the complexity.
Okay. All right. So basically, we're talking about tens to roughly hundreds of runs before you think like, yeah, the ML now has all the data points to optimize, and then that can continue. Basically, you have a model for that workload, and you can go on and on and on. Until at some point in time, people say the workload has changed significantly, so it's time to
restart. Yeah, let's say that if you start to work again on the same workload, you can reuse the previous knowledge because it's a similar problem. But if you change the workload or change the code, the Spark code, let me say application code, it is better to start a new optimization from scratch because it's a completely different problem. So if the problem are close one to the other, you can reuse the knowledge of the previous one, so the model can be reused. Otherwise, it's better to start from scratch.
Superb. Thank you so much, Luca. Let's see.